and I'll request control again. Okay, good. There we go. So I'll first introduce us a little bit. So thank you very much for having us, first of all. So the four of us present today are part of the CFD methodology team at McLaren Racing. So what we are looking after is the whole pipeline that is being used to do external aerodynamic and cooling simulations for the Formula One race car. So we are only working for the racing side of the McLaren business, which also has an automotive and applied technology businesses. So we'll be focusing solely on that side. So purely all of the work that we are doing is about fluid dynamic simulations for all different race car categories. So I am Julian. I'm currently the head of CFD, and I've been in McLaren for about 10 years now in different roles, all CFD related, and did a PhD before that in numerical methods. Really, we also have Adam Swift, who's currently project leader for the CFD group. And as well worked for the STL and did a PhD as well in aerodynamics before. And we have also Athanasios, who's the CFD project leader as well for McLaren Racing, and did some different consulting missions before joining McLaren, and as well did a PhD in numerical methods at Imperial. So that's us tonight. And so what we'll be focusing on is mostly the racing side of the business, but as I was mentioning, we have also the automotive group and the applied technology sections. But because of time, we'll focus mostly on what we do most of the day, which is the Formula One side. So as you can see here, the racing business is evolving a little bit. So we have currently 3 competitors. So we have the Formula One, which is our historical car. We have IndyCar, and we have also Extreme that has been launched recently. And basically, the CFD is going to be used across those 3 environments, perhaps a little bit less in Extreme because of the rules. But the idea is that our group is providing a service for aerodynamicists to design these different race car categories. So we spend, let's say, 99% of our time in Formula One, but we also have some interaction with the IndyCar sections and the Extreme. So some numbers first, we go quickly through this. So we are still the second most successful team in history, 183 victories, and we've won pretty much all of the categories in racing. That's our current constructor championship ranking. So we finished 3rd last year. We've had a couple of tougher years before that, but hopefully we are now on the right track back. And then we'll go through quickly some numbers to give you a bit of context on what the Formula One Championship is really. So it's a global sport, right? So it's across multiple continents. We have 23 races during the season, 17 races in 2020 despite COVID. So despite the fact that all of the world was kind of in isolation, we've managed to do 17 out of our 20 races through that period. So that's 10 teams, 20 drivers, and 4 engine manufacturers. And some of the things that we will discuss is what makes our business a little bit different to anyone designing cars. Really, is the fact that it's a sport, right? So we have technical and sporting regulation, and we also have a budget cap. So all of those are to try to make sure that we have as fair a championship as possible, and just to make sure that you cannot buy your way to success in Formula One. So this budget cap was introduced, and that's the first year we're in the budget cap, and basically we'll slowly reduce that budget. Just a quick question: can you see the last line of that slide, or is it because I can see the zoom?
I can, yeah.
The zoom line on top. Okay. That's okay then. Good.
You mean previously $450 million?
Yeah, exactly. So it's been wiped out on my screen, but I just changed. Okay. What is a typical Formula One weekend? So that's a good example. It's Spain, the pre-season testing. So we'll do a race weekend. We'll have 3 one-hour practice sessions before qualifying, and that's pretty much the only time we'll have to actually judge our car on track, right? and then we'll have the race weekend will start, and those restrictions are getting more and more stringent. So we have less and less with what we call the winter testing, which is the pre-season testing, where we can kind of troubleshoot our car and make sure that everything works as expected. But because this time is reducing for budget reasons as well, this means that we have to rely more and more on our simulation tools to make sure that our car arrives in a state that is as ready to race as possible, really. Okay. In terms of performance, the gap is fairly small. So we have 10 cars within 2% of the lap time and 20 cars within 4%. So that's the kind of envelope we're talking about. Okay. We have also fixed timetables, and there's nowhere to hide, right? So the performance is publicly assessed 20 times a year. If the car is not good enough, everybody sees it straight away, right? And yes, so that's all of the standard things that you can think of. So we'll be judged on the driver's performance, on the car's performance, pit stop, strategy, reliability. All of these come into play for us. Adding up a bit of a few numbers for context there. We have a car that evolves through the season. So pretty much each of our car, we only build 2 years, right? And each of them are prototypes. So it's purely research and development, and it will evolve across the tracks. Some of the time to try to adapt to the circuit, and some of the times just to try to bring performance slowly in increments. Okay. The weight of the car is only 750 kilos, and with driver but without the fuel. And in comparison, we generate up to 3.5. Let's say 3.5 is a good estimate. Tons of downforce at max speed, right? So we're generating more than 3 times the weight in terms of pure downforce. The max speed is around 360 kilometers per hour. And yeah, there's a few additional numbers there. One of the ones that is quite interesting, if you think about reliability, is the number of gear changes in a single race, so more than 3,000, and the G-force and underbraking that you can see. So you have some numbers there, and there is a video that has been shared of which is always quite instructive, is to show the kind of training that the drivers have to go through just to be able to make sure that they resist this kind of cornering, this kind of G-force that they will be submitted to during the race. So there is a very specific training to reinforce their career. Okay. As I was mentioning in the initial slide, another thing that makes our sport a little bit different is that it is a restricted activity. Okay. So we'll spend a little bit of time to explain this, because this is not something necessarily that you are fully aware of from the outside. So F1 is a sport, right? And as such as rules, the goal is to make it sustainable and to keep the gap between the teams as close as possible. And so we've had this first cost cap introduced this year to make it a better level playing field. And so that's a new thing, the cost cap, right? So because we used to have disparities of budget between the team, which you can see on pretty much any professional sport, right? There's always going to be teams that have a slightly different budget, but basically we are trying to go in a model which is slowly dropping in terms of overall budget, so that the smaller team can join in, and the larger team have to kind of reduce their spending a little bit, so that we get a bit closer together. So that's something new, the cost cap. But the technical and sporting regulations have been around since the beginning of the sport, really. And the sporting regulation, the technical regulation restrict what we can and cannot do. So they kind of give us constraints as to how we design the car. That can be simple things like the number of wheels, etc. All of this is written down, right? But then you have also some things that are much more constraining in terms of aero development. So we have what we call legality boxes. So regions in space that are defined with respect to the 2 wheels and the 2 axles, where we are allowed to put aerodynamic device like winglets and different devices. So this is a very stringent set of rules, and basically we need to try to maximize the performance given the set of rules. So that's the technical regulation. And then we have the sporting regulation as well. And some of those are directly applicable to us. So because aerodynamics performance is so important to the overall performance of the car, it is a regulated activity. So we have strong limit in terms of the way we use CFD and the way we use the wind tunnel, and I'll go through these in the moment. Another thing is that because it is a regulated activity, it's also an audited activity. So we regularly have audits from the FIA coming in to just check the logs of all the simulations we're running, checking how we use the wind tunnel, etc., just to make sure that there is no infringement. Okay. And the other thing that will be discussed a bit more in the next section will be the change of rules for 2022. We have a big change of rule from this year to next year, and we'll discuss that a bit further. So if we go towards if we talk about the limitation, so we have a maximum of 320 wind tunnel runs for each week period. So our year is divided into 8 weeks period. So that's 6 8-week period over the year, and there's a couple of them that are slightly longer. But basically, over those 2 months every time, we are allowed to spend about 320 wind tunnel runs, a maximum of 80 hours of wind tunnel time, and a maximum of 400 hours spent in the wind tunnel. So what we call time spent in the wind tunnel is time between the moment of the first run and the last run. So this is to make sure that you don't you can potentially share the wind tunnel so that you don't stay there to do long changes. And the 80 hours, it's the amount of fan time that we are allowed to use. So that's we consider fan time every time the wind tunnel fan goes about 50 meters per second, or peak speed is 50 meters per second for a 60% model, which gives us Reynolds numbers that are fairly similar to what we see on track. And so those additional constraints are there to reduce the cost of wind tunnel usage. So reducing the time we spend on the wind tunnel, and as well reducing the number of distinct configuration that we build for the wind tunnel. So 320 seems like a big number, but if you look at the size of our parameter space, which we look after, you'll see that it's not that big in the ecosystem. So basically, the idea of this set of regulation is just to make sure that we don't design too many parts as well, that we try to be more efficient with what we are doing. And what is interesting in terms of making the championship as fair as possible is the fact that there is no scaling factor applied depending on your position on the championship. So basically, in January, we will check what is the position, what was our position on the championship last year, and in July we'll update this again. So let's say if we put ourselves in the situation of 2021, we finished 2020 third, so we knew that we were losing about 5% of our overall budget for development on the next year. Those restrictions will get much more severe next year, and that will be applied from 2022 to 2025. And let's say the first in the championship on any given year, we lose almost 30%. We lose not almost, exactly 30% of their development capacity. So that's a fairly big incentive, and that again, the idea is just to help the smaller team potentially that have less resources or less sleek processes or less efficient processes to get a little bit more throughput to try to help them close the gap. So that's what happened on the wind tunnel side. And then we have the equivalent on the CFD side. So we have 60 million allocation unit hours. So you can think about it as core hours. So we have 60 million core hours, 6 million, not 60, sorry, per 8-week period. And the only difference is that this is not pure core hours. So this is not just the number of cores time, the time you spend on the cluster, but we also have the frequency as a multiplier, because otherwise you would do as you do with machines, your local machines, you will try to overclock the machine to get a bit more power. So just to avoid this, we have this frequency coming as a multiplier. And again, we have another restriction, which is the number of independent geometries, so 2,000 geometries that we are allowed to run in CFD. So every 8-week period, we only allow 2,000 what we call RATG, so restricted aerodynamic testing configuration. And if you need to think of it as a car on track, a configuration on track. So we can, so that's 2,000 independent geometries that we can test, so different settings, but we can run them at different attitudes. So we can run them in different conditions on the track. We can run them in cornering or in braking condition, but we only are allowed to test 2,000 independent geometries. And so what this means is that, let's say, different projects like design of experiments or fully automated optimizer are prescribed for us, because this is not necessarily the most efficient way to use those 2,000 geometry. And if you consider the situation of fluid structure interactions, so FSI, let's say if you consider that your wing is evolving while you under load, right? It's deflecting under load. And if you were to run a transient simulation of this, every time step that you will be running while your geometry will evolve because of the load, you will in theory use one of those RTGs. So it's very inefficient to run this type of simulations with those new rules. And one last constraint that we have, and which is the reason why we spend quite a bit of time looking at the HPC side of things as well, is the fact that we are also prescribed on the type of hardware that we can use. So for instance, GPUs are explicitly banned. For us, we know that it's a trend that is developing more and more in modern CFD codes or codes developing in research. But for us, because there is no clear definition or clear equivalency between CPUs and GPUs, something that you can frame within the same rule set, they've decided as a way to just make sure that there is no loophole in the rules to ban the GPUs. Okay. So that's pretty much the context. And so the reason for all of those restrictions is that, let's say, when CFD arrived in F1, we quickly realized, because aerodynamics is the biggest performance differentiator, right? So it started really an arms race between the different competitors. And we were in 2004, 2005, we were at the bottom of the top 500 in terms of the CFD capacity that we had. So we had those 25 teraflops, which is just a measure of the size of your cluster, an efficiency measure. And at the time when those rules were first implemented, this corresponded to the bottom of the top 500. And so what the FIA has done is that to limit the arms race in terms of just buying more and more computer resources, is that they fixed this size. And we've kind of stayed flat since then. So we benefit from the gains in efficiency from new generation of CPUs, let's say, but we have to stay within that budget. So we cannot just buy a bigger cluster to just try to run more analysis. So this is the reason why efficiency is paramount to us, and it will have an impact on all of our choices down the line. Okay, it will have an impact on our choice of methods for solving the Navier-Stokes equation, and an impact on the way we use our resources. Okay. Thanos, do you want to take over? Yeah.
Yeah. So thank you, Julien. We will continue with a few points about aerodynamics development, and oh, I don't have control. Sorry. Need to stop sharing. Apologies. It was about to happen. Come on. So let's talk about now aerodynamic development in F1. And as Julien mentioned, aerodynamics performance is the key differentiator in Formula One. Formula One car is a highly complicated system, and everything helps in the performance of your car on track. However, I think it's common knowledge that potentially, if you want to do big steps in your performance on track, probably you have to improve your aerodynamics. And it's not straightforward, because a car is a very complicated system of physical flows, and about how different vertical structures interact from the front to the rear of the car, how you load different parts of the car influence other parts, and etc. So you are trying to add a performance by trying to deliver efficient downforce levels. Efficient downforce by meaning that you want obviously to increase your load, but you don't want to do it by adding extensive drag, right? And on top of that, you try to achieve this by offering to your driver a drivable downforce. No matter how efficient you are, if you have switches of state, let us say in a corner, your driver will not be confident to either brake later or commit to the corner, and you will lose time. And it's very complicated because not only you have to do it in an efficient way in a generic operational envelope, but essentially you have a sub envelopes of operation because you have different tracks. You can go here, we have a picture of Monaco, which has something like nearly 20 corners, very low speed corners. You don't have big straights. So your aerodynamic operational envelope here is completely different from what you get, for example, when you go to Monza that we present here. Monza has 11 corners, but for example, Parabolica is a flat out corner. You have Lesmo, which is a flat out corner. So essentially, you have maybe 1, 2 S's and Ascari that you are not flat out. And you understand that the requirements of an efficient car are completely different there. And how we achieve an efficient, an aerodynamically efficient car, obviously we use 3 environments. First and foremost, you have the track where you are judged about your performance. But the conceptual development of a Formula One car is done in a wind tunnel and in a CFD environment. And usually you will see aerodynamic departments having something between 60 to 100 people, depending how big a team is, working in trying to optimize and deliver the best possible car in aerodynamic terms. And going back to efficient downforce and how important it is for your car to be aerodynamically efficient in a track environment. Here we will talk about aerodynamic performance and how you have to deliver performance in different attitudes and states of operation for your car. Here, if you imagine that we have an x-axis, that it's the distance from start to finish around your track, we have on the right-hand side the speed that you carry at each position. And you will see 2 traces. Let's call it competitor A and competitor B. And you also have a third axis on the left-hand side, which shows you the delta between the 2 cars. And so if we go through the different stages, here you have a straight line. Both your competitors accelerate, and you see that competitor A, noted by the black line, delivers higher speed and also brakes later than competitor B. However, what we will see is in the first corner, your competitor B maintains higher speed. And this is the trend more or less in all corners that are above 110, I would say, kilometers per hour. And although your competitor A in all straights is quite faster, you will see that eventually competitor B is 0.4 faster, seconds faster than competitor A. And this highlights the importance of different states towards your overall time. If you notice, competitor B maintains higher speed in corners, and you can clearly see that your corners have higher sensitivity towards your overall time. So as aerodynamic department, we need to make sure that not only we maintain high levels of speed around straight lines, and we have high top speeds, but we also performing different kinds of corners and states. For example, here you have a high speed corner. So you reduce a bit your speed, but you don't have to brake significantly. You have low speed corners, and you see that the operational envelope is very complicated. And on top of this, even when you don't have big aerodynamic changes as we do from this year to the next, even when your car is a continuation of the previous year, you have to take into account that you need to perform along different operational states as well. We mentioned before, we have a Monza, which is a very low downforce circuit. But on the other hand, you have Monaco. And on top of this, you have a circuit like Mexico, where you have special requirements related to cooling. And your development throughout the year never stops. It's not unheard to bring new parts to races every second weekend or every weekend. And this highlights how difficult it is for an aerodynamic department to deliver constantly in the pursuit of more efficient car. And I mentioned before, the aerodynamics of the Formula One car are coupled. And this is a very unique quality about Formula One. What you do at the front, it's 100% sure that it's going to influence your rear car performance. So every design decision is very thoroughly thought of. You have a vortex at your front wing, and the impact is tremendous at the rear. Famously, the Y250 can switch your entire floor on, or if you are not very careful, can switch it completely off. And additionally, you have more things to take into account. You have your DRS open or closed. we mentioned that you have low speed apex corners, high speed apex. You have to take into account braking, acceleration. It's a highly complicated system. And Julien mentioned before that you have prescribed legality boxes from the regulations, but this never stops us from generating thousands of geometries per month. And why is this possible? Apart from conceptual changes that you want to change something and you make big changes. So for example, you take, if we look at this rear wing end plate, a conceptual choice would be like, are you going to slot it, or are you keeping it as a one-piece solid geometry? On top of that, here you see typical changes that have taken place for 34A, which is this car. And you see, you can hardly see the two geometries. We are talking about millimeters, but this change for the world of Formula One is a very big change. This can have a very big effect in your overall aerodynamic performance. You see a top wing here. The concept is the same, but you are always trying to locally optimize, prevent local separations, improve efficiency, and etc. And how we do this, how we deliver an efficient car, we work together, aerodynamicists and CFD specialists. We are CFD specialists. And our aim is to deliver the better aeroflow modeling and management that we can to aerodynamicists, so they can optimize lift drag trade-offs and perform in aero performance context. And to do this, we have CFD tools and methods that we work on, and we have experimentalists that work in a similar fashion, trying to optimize the wind tunnel and track methodologies. Okay. So, what about the life cycle of a part? Usually you will have a conceptual idea, you will design this in CAD, and your first reading will come from a CFD simulation. And you will spend quite some time in this loop. So your initial idea will go to CAD, you will get your initial results. It's highly unlikely that you hit your target with the first go, no matter how experienced and how smart you are. And you are in a continuous loop trying to locally optimize, change your concept if necessary. And once you have achieved your performance targets, then you send this part to the wind tunnel. You will get a wind tunnel run that you will have to analyze. And depending on your results, there are still two avenues. If you are happy, you can send it to the track for a test. Or if you see that for maybe miscorrelation reasons, the part still needs work, essentially you are going one step backwards and you are re-entering the design loop. Once it's at the track, if Lando says that everything is okay and you perform, usually in a Friday testing session. Everybody's happy, you have good correlation, and hopefully, yeah, you perform well. But it's not unheard that your part is not delivering what you have been expected from CFD and both wind tunnel, because there are different reasons of miscorrelation. But this doesn't necessarily mean that your concept has completely failed. Usually you will go back and with the knowledge of even this miscorrelation, you will try to address the hiccups that you had and hopefully come up with a better design that delivers both in tools and at track. Regarding wind tunnel, we are running a 60% scale model with bespoke Pirelli tires, and your maximum speed, fan speed, is 50 meters per second. We have model motion systems to replicate your roll, pitch, and steer. So overall, you have a good capability of replicating track conditions. Radiator and exhaust flows can also be simulated, and you have a fully operational suspension. And your model is fully loaded with any sensors you may need. Pressure taps, forces, PIV, and other laser techniques are all available. Wind tunnels use a rolling road technology, so your ground is moving. You have a stationary model, and obviously your fan blows air towards your model. One other detail that highlights how complicated the world of Formula One is. So, for example, you have only changed this foot plate. Are you going to create a fully new front wing? No, you want your surfaces to be very modular. So if you change a part, you want to be able to change as much as possible on your wind tunnel model. This allows you to have less downtime, perform changes faster, and be more efficient. And we mentioned that the wind tunnel operates at 15 meters per second. So you will start your run, your fan starts accelerating, you will reach an airspeed of 50 meters per second. And while you are changing the attitude of the car, replicating different attitudes, you can even replicate very closely complete track conditions of a specific part. But you can see that the airspeed is maintained at a constant speed, so you don't have a reduce of airspeed or acceleration, and etc. Regarding track, which is what matters, right? No matter if your geometry performs in CFD and wind tunnel, if you don't perform on track and it doesn't prove its worthiness, it doesn't matter. However, you have to take into account that track conditions are full of uncertainties, right? Even when you do back-to-back tests for a geometry, and this is so you go around the track with front wing A, you come back to the pitch, you change the front wing to front wing B, and you straight go out. So the rest of the car stays the same. No one guarantees that your track conditions are exactly the same. You cannot control this. So track tests are usually more clouded because you don't have control of the environment, and usually they take more time to analyze and come up with a judgment about component. This doesn't stop us from having different measuring techniques even at track. So here we have a rake, but you have to take into account that you have a very limited track time on Fridays and Saturdays. So you have to take into consideration the other work that needs to be done in terms of car setup. So you cannot request rakes to be run every time and all the time. You also have flow-based opportunities, which is also very important, and you can locally judge your components. The only disadvantage of flow-based is that usually other teams can see your flow-based too. So yeah, you have to hide it sometimes. And we talked about wind tunnel and track testing. Adam is going to continue later on with CFD, but the decision making is the following. You go from CFD to wind tunnel and track, and hopefully you are operating where these three environments meet. So this means that you get on track what you expect from your tools, and hopefully this is a better component. But I mentioned before, sometimes good components in your models don't necessarily translate in good components on track. But this is still very important because it can address miscorrelation issues, and it's been fed back to the design of the modeling. So it's a continuous back and forth between models and track, and a feedback loop, if you wish. And why is Formula One so difficult, and especially in aerodynamics? One of the main reasons is this pretty wheel here, right? It's a luff body, it's a rotating luff body. So its weight, it's highly unstable. And essentially these, the amount of losses that you generate here dictate your downstream performance. And just to give you an idea how unstable this area is, we have here an unsteady simulation that shows the amount of unsteady. So yeah, essentially, if you want to improve your car performance, you have to control the amount of losses of the front wheel weight, and if possible, to mitigate all this, which is easier said than done. Regarding changes of regulations, next year we have a big complete change of regulations, and the cars will not look the same as we have this year. We have some striking differences, especially front wings no longer produce a Y250, which is one of the current prevalent vortices that dictate your car performance. You have restrictions in the number of elements that you have, and yeah, you have a wheel arch here, which all these changes aim to essentially bring the field together and allow overtaking, facilitate more competitive racing, and hopefully produce a better show. Adam?
Hello. Let me take control. Control. Thank you. Yeah, one thing Thanos mentioned before was about FlowViz. One of the cheeky things that F1 teams tend to do is if you use UV sensitive paint instead of the fluorescent bright yellow ones, you can only see it under UV light when you got back in the garage. So sometimes you might see that it look a little bit grey, not really be able to see what it is, but back in the garage it looks awesome. But anyway, that's just a side note. So hopefully we still got everybody. Let's see if this works. There we go. Okay, so I'm going to talk a bit more about CFD in Formula One, which is obviously our main specialism here. Okay, so just distracted by the chat. Yeah, so CFD is massively important to us in Formula One, because you get different information from CFD versus, say, wind tunnel. So with CFD, you get the full flow field with the with all the vortex positions, the wakes, and all this sort of information is massively useful for developing the car. Whereas the tunnel can give you some of this information, but there's always a compromise. Any tool that models something is always a compromise. One of the compromises of wind tunnel, if you want to measure something, it tends to be intrusive. So like putting in a rake or putting in a probe. In CFD, we don't have that limitation. We have the different ones, which we'll go into in a minute. But having the full flow field to go and use to design your car is incredibly powerful. And we can simulate the track, and we can simulate different points of the lap. So, for example, low speed corner, high speed corner, braking, DRS open, closed, etc. Thanos, could you just skip to the next slide? It doesn't seem to be working for me. Is it working?
Adam? You're here.
Can you hear me?
Yes, we can.
Yeah, we can. Yeah.
Thanos, could you skip to the next slide? I can't control it. I can see my cursor, but I can't do anything with it. Thank you. So just get everything up on the screen, please. Thank you. Yeah, so this is the safety process. So you start off with having a great idea on how you can design your car. You design it in CAD. We typically only do half a car because it makes things more efficient. Once you've done that, we have to chop it into millions of little tiny cells. And then in each one of those cells, we solve a discretized version of the Navier-Stokes equations, which give us these beautiful, pretty pictures. So this is surface pressure over the car, along with total pressure along the slice. And we can use this information to go and design our car. So from that, you go back improve your design, and you keep going around this loop until you have something that you believe is good enough to send to the wind tunnel or send to track. Oh yeah, and this entire process is pretty much automated, other than obviously analyzing results, which you have to do by eye or by numbers, and doing the CAD, obviously you have to get your hands dirty. But once you've done this, most of it's just a button click, make it nice and easy. Okay, so challenges in F1. So the flow through around the car can be anything from laminar to fully turbulent flow. We have large physical and temporal scales because the car's about 5 meters long, 2 meters wide. But if you look at the trailing edge of a wing, you might be sub-millimeter in thickness. So that gives us quite large, quite different scales if we have to go mesh and simulate. The aerodynamics around the car are highly complex. So to generate the most downforce, you want to have your wing elements as close to the edge as you possibly can without going over the edge. So you want them as loaded as possible. We use vortices to manipulate the way the flow goes around the car and also to generate extra load. But they have to go through both favorable pressure gradients as well as adverse pressure gradients, such as going around the tire. We have buff body separations, such as a tire. We have to deal with the mixing of hot and cold flow, for example, your exhaust flow or the flow of hot brake discs. And there are other areas of the car that you can do conjugate heat transfer on, or say aeroelastics. So no matter how stiff you try and make a front wing or a rear wing or a floor, they always deflect because of the huge amounts of load that we're putting in. As Julian's mentioned before, we are quite restricted in the amount of running we can do. So we have to be as efficient as possibly can, efficient with our methods as we can, and try and get the fastest turnaround time. Because if you can do more designs, you can try more ideas, and you'll end up, so to get a design onto the car, you tend to do a lot of different experiments before you get to that point where you think it's worth committing tens of thousands of pounds to actually build it, because things are expensive. So how do we make the most of the rules? Currently, we rely heavily on Reynolds average Navier-Stokes modeling because it's the fastest of our methods. We do like DS or unsteady methods, but they're a lot more expensive. So if you've got a certain amount of computational resource, you need to be able to justify why you need to use that expensive method to design your part versus using a cheaper method. Things we can do to improve things are we can optimize our mesh to make the mesh as light as possible while still giving us the correct answers. There's things we can do to tune the numerical methods. So you can change like things like your URFs, your CFL numbers, things like this to go and make simulations run quicker. And obviously the model's only any good if it actually matches track. So we spend a lot of time figuring out what we need to tweak to make sure it matches track. We are allowed to do methodology development. So this is CFD development of the method. So do we use RANs with this turbulence model or that turbulence model? What happens if we change this parameter? But we can do that on old cars, so 30 months old. It's almost getting near 3 years. It's an old car. I don't think we're allowed to change the geometry anymore, but we used to be able to. Well, when I say change the geometry, it was only about meshing. They got very upset if you actually tried to change the geometry because you're not allowed to design the car doing this. Yeah, so we have a full spectrum of turbulence modeling that we could do or would like to do, from RANs on the left, which is the cheapest method, DS, which is still sort of sits in the middle, which is unsteady, gives us a lot more information. And we're using both of these in Formula One at the moment, along with our competitors. What we would like to do is go towards the higher fidelity models like LES, but they are expensive, which we'll get onto in a minute. But as you can see, as you go along through these different methods, you have like a smeared out steady state solution to a solution with a lot more of the eddies and vortices, which, well, not vortices, but eddies, which you get vortices in this as well, which gives us more information when we're trying to design our car. And this just has even more information in the solution, which is what we'd like to be able to do. But at the moment, it's too expensive given the rules we have. So starting at the beginning, Reynolds average Navier-Stokes. So this is taking the Navier-Stokes equations and averaging them with respect to time. When you do this, you end up with a bunch of viscous effects that you can't neglect. So we need to have a viscous solution, because we can't pretend it's inviscid. But by having viscosity, you have turbulence, and turbulence is a problem. When you do your Navier-Stokes averaging, you end up with some viscous stresses that you need to model, but you don't have enough equations to solve the whole system. So that means you have to add in some extra equations. So we tend to do what's called the Bolognese approximation to make that problem simpler, and then to calculate this new turbulent viscosity, we then have to go and come up with a model. So there's many models out there. These are some of the more famous ones. So Spalla-Amaris, which is a simple one equation model, where you add one extra equation into your set of equations to solve in each cell. The very popular K epsilon, K omega, and K omega SST, which are the common 2 equation models. And then if you want to solve all the Reynolds stresses, you can add an extra 7 equations in, called the Reynolds stress models. And if that isn't enough, each one of these models has lots of, say, variants of them. So for the K epsilon model, just for example, there's the realizable K epsilon, 2-layer K epsilon, elliptic blend K epsilon, lag elliptic blend K epsilon, the AKN K epsilon, and V squared F K epsilon. And then if you go to the other ones, they'll have other variants as well. Each model has a number of strengths, but also weaknesses. And because you're trying to solve something incredibly complicated with 2 equations, or you're having to simplify it to solve it. So there's no perfect turbulence model. One will work, say, for your vortices, get your vortices modeled very well. Others will model the wheel wake really well, but none of them really model everything very well. So this is an example between 2 off-the-shelf turbulence models. I think they're both 2 equation RANS turbulence models. Looking at the Y250 vortex and a fence vortex. So over here is this is the Y250 vortex. So this is the vortex coming off this is the Y250 junction, and we spin up a vortex here which goes along the car, which goes around the back of the wheel and out by the side of the side pod. It's incredibly powerful. It generates a huge amount of downforce, both mainly indirectly by helping other bits of the car make even more downforce. It's an awesome structure. So this is showing pressure, and then this is showing your total pressure, or the coefficients at least. This shows that this turbulence model makes it a much stronger structure and a much cleaner structure compared to the first turbulence model. So it just shows that depending on what model you choose, depends what answer you're going to get. So you have to make sure you choose the right model that gives you the best outcome for the thing we're trying to model. And it's not a trivial or easy answer, which is great because it keeps us in a job. So this is another example, again, looking at 2 different turbulence models, probably the same ones we saw in the previous slide. And this shows the front wheel wake. So you can see this is the loss. So this is coming off the front wheel, and this is going to hit if you're not careful, could hit the back of your car and you lose a lot of downforce. So this is why this is one of the most important parts of the car, is trying to make sure that you get control of this front wheel wake. But it again shows that depending on which turbulence model you choose, depends on what answer you get. So as you can see up here, top of the wheel wake, it's got a very different shape depending on which model you choose. So correlation is incredibly important with what Thanos showed before with the rakes, because you can go and see what it looks like a track in the wind tunnel, and then you can also do an equivalent of a rake in a CFD to go and make sure the 3 environments match as best as possible. Once you've decided you've chosen a turbulence model, each turbulence model has lots of coefficients you can play with, and this is just an example. We're not going to tell you which coefficient we're playing with, but we've got 4 different values of this coefficient, and as you can see, they have 4 different answers. By tweaking that parameter, it changes what the answer you get is. But that could be potentially used to help calibrate your model to make it more applicable to our specific application. Because turbulence models tend to be general purpose. We're not after a general purpose. We're after what is best for an F1 car. So we're happy to make compromises where it might not work very well in a pipe, but if we're not modeling a pipe, we don't really care. So this is exactly what I just said. So we use rakes to go and check to see which one of these solutions look most like what we get on track. Oh yeah, but that's an important point. We can only check we're right once we've got the car running on track. We can't check we're right beforehand because, like in we might have a design for the 2022 car, and that's being built at the moment. But until we actually get to run it on track in February, we just have to hope that all the sensible decisions we've made about how we model the car are right. So the other end of the spectrum is large eddy simulation. This is, instead of averaging your equations in time, you kind of average them in space by making a coarser grid than what you would need to solve the equations directly, which is called direct numerical simulation. And to put that in perspective, to do a channel using direct numerical simulation, you might need 191 billion cells for a small channel, in which case, if you imagine an F1 car is a lot bigger than a small channel, we're going to need a lot more than 191 billion cells. So what you could do is make the cells bigger, so you use less cells, and then use a subgrid model to sort of model what happens in those cells for turbulence, which effectively means sort of like dissipating out the turbulence, because the largest eddies are the ones that contain most of the energy and contain most of the information, and then the smallest ones away the energy. So the smallest eddies, called the Kolmogorov length scales, are the ones which dissipate the energy off into heat. So at the moment, although we desperately would like to go and run this model, we can run maybe up to 8 in every 8-week period, so maybe 1 a week, but you can't really design an F1 car with 1 simulation a week, which is why we haven't started looking at this yet. But there's a compromise, and this is called detached eddy simulation. This is where you go, well, the most expensive bit of a large eddy simulation is where lots of interesting things are happening, which is next to a wall, which is like on the surface of a car. So what you could do is say, if we run LES away from the wall, say like in the wheel wake, where we want to know what's happening with all these complicated structures, but near the wall we'll use RAMs because it's cheaper. This could be a good compromise in respect of the amount of computational effort you have to spend for the result you don't get. So this is what we actually do. Yes. So it's kind of the best of both worlds for cost. And this is an example of a DS simulation. So this is a quick comparison between the 3 methods, which you've kind of seen a bit before. So RANS is our steady state ones, which is actually very good. You can design F1 cars doing this, and most F1, pretty much the F1 cars you see on the track today are designed in RANS, but with some DS simulations. When you believe that there's a bit of extra important information that you need to get from a DS simulation. LES, again, is what we'd love to do, but at the moment it's just too expensive. But you know, clever people at universities and stuff are working on trying to figure out how to make these things cheaper and faster and better. So you never know. Within my career, I expect to see F1 cars being run in LES at some point. I think I've covered this as we've gone along, really, saying that the most important thing for what we do is having a robust simulation. So as in, when an aerodynamicist designs their car and clicks play, they get a result every time. If they run the same case twice, they should have exactly the same answer twice. Because if they get a different answer each time, that's not going to be any good for them. And then finally, it's got to be accurate. And also very fast. So yes, as I said, we tend to do these smaller models if we can, or the cheaper models if we can. So that sort of covers the presentation. So it's open to questions now, I think. I think we've got one extra slide. I don't know if Julian, you want to cover that?
Yes, I can do. Yeah, just a quick catch up. We were expecting. I don't know if Richard has joined us or not at this stage. No. Okay.
I don't know.
No. Okay. Good. So I'm just mentioning this because there are a few opportunities if you're interested in joining us, depending on where you are in your career. So what we've been doing in the PhD group in the CFD group for a few years is this PhD internship program. And so basically we are looking at students doing their PhD in their second or third year, and we're doing a 4-month internship, so you will be fully embedded within the CFD team. And we look at this as a way to tackle different projects that are of high interest to us, looking at the aerodynamics, CFD, machine learning, and NR CFD and HPC. In the recent years, more than 5 interns have earned a full-time position after completing their PhD with us. So it's a good recruitment route as well. We also have an engineering graduate scheme, which is the closing date for this year's is in a couple of weeks. So if you're interested, you need to just go to the McLaren career page.
I think it's 1 week from today, if I'm not mistaken.
1 week from today, you're right.
Yeah, a little bit less. So interested students still have time, I think.
So the graduate scheme is a very nice program because you get involved into different areas of racing before you kind of finalize your choice of the area you're more interested in. And so you will potentially have a chance to work on the strategy team, on the CFD team, on the aero development team, on the stress and the marketing, all sorts of different placements just to understand the way the company works really. We then have those 1-year engineering placement and also summer placement from time to time, but that's a bit more rare. So if you have any questions about this, you can always contact us, and there's also the career website where all of those, it's careers.mclaren.com, where all of those offers are always published. Yeah.
Could you stop sharing your screen so that we can see everyone?
Yes, of course.
If you have a question, just raise your hand, and that will be easier. Ludwig? Sorry if I mispronounced it.
No, it's close enough. Thanks, man. Hi. Thanks for giving me the opportunity. The talk was fantastic. One of the best I've ever been to. Thank you so much, first of all. So I think my question is with regards to integrating of the CFD and the FSI simulations you've been doing. So McLaren's and all of that, along with lap time simulation softwares which the team use. So essentially to create aerodynamic maps. So I think my question is, do you do that for basically like 1,000, 10,000 simulation iteration for every single iteration improvement? Like for example, you improve the barge boards and the front wing to call it an improvement, and the rear wing along with it. And you run that for every, yeah. That's sort of what my question was. Thank you.
So I'd say it's a funny world working in Formula One. It's very much about the rules. So if we were to deform the wing, like do FSI, then that would then count as another aerodynamic simulation, new geometry, which will count against our limit, because now that you've changed the shape of it, so it's a different geometry. Because the FIA would argue that how do they know that that's a aerodynamic deflection due to load versus McLaren's brand new, super duper new front wing that is actually deflected 2 mil. So you can't. Sorry.
So in short, you can't do it over multiple lap. You can't do multiple lap time simulations for each upgrade.
it depends what you mean by lap time simulation. If you're doing a sort of 1D is going to be too harsh, but say like a 1D lap sim, it's not an aerodynamic simulation, so it's nothing to do with sort of us, but it is for the race department. The vehicle dynamics department, they will do lap sims, but not to the level of complexity you're describing with FSI, which is
okay. So those aren't
for anyone else. Yeah. So.
Okay. Yeah. Question, because I wanted to know if CFD was integrated with the vehicle dynamics department's lap time simulations, essentially.
In theory, you can, but you need to be very careful, as Adam mentioned, of how you use your RATGs and your MAUAs, because obviously to run a fully coupled FSI CFD simulation, probably you would run it in transient mode. So it's expensive both in geometries that you consume and simulation time. But yes, we have this opportunity if we wish to pursue this avenue. We just need to be very thoughtful about how we use these opportunities, if you see what I mean.
I guess the only thing I'd add to that is we have lots of different tools at our disposal, and CFD would not necessarily be the most sensible decision to go and pass information to the vehicle dynamics on, say, an aero map.
Okay, that answers my question. Yep, thank you.
And finally, the effect of fluid structure interaction is kind of restricted by the rules. So we have some control tests applied by the FIA to just try to limit that effect to the maximum, which to a certain extent desensitize the car to those effects. So it is an important effect, but it can be second order to a certain point. If you were to do a lap simulation, maybe it's not the first order element that will drive the accuracy of your model. Yeah.
Awesome, thank you so much.
There was a question in the chat if the graduate scheme is open to UK residents only.
If I'm not mistaken, it's not. It has some visa restrictions. So if again, please do double check, but I think EU citizens who have settled status probably qualify. Overseas students who have a visa potentially qualify, but please do double check. I'm not 100% sure.
Right.
For the graduate scheme, yes, I would
sorry.
suspect. But for the graduate scheme, I would suspect, yeah. It should be described online. Yeah, we were supposed to have someone from our team to cover those questions, but we can check in the background. Yeah.
Right, Finn.
Hi, I just had a quick question. What is the most challenging track, aerodynamically speaking, to set the car up for?
The short answer is that it depends on your car, basically. I know it sounds a bit like an answer, but different cars, and you can see it with the way during this session, the way the ranking of the different teams has changed quite often during the different races. So you have each car has those strengths and weaknesses, and potentially the worst track for you is the one that exposes the strongest the weaknesses of your car. And you can see if you check a little bit the results of this year, even if you don't consider accident-related events, you will see that certain teams start to come into the foreground on certain type of tracks and not on others. In terms of the one that is the most taxing for aerodynamics, it would have to be Monaco, right? That's the one where we require the maximum amount of downforce, and where potentially there is more incentive to actually put downforce, even if it's not efficient in terms of the drag that goes with it, really. Yeah. So yeah, to answer your question, it really depends on the limitation of your car. Yeah.
Brilliant. Thank you very much.
Nicholas?
Hi. So just a quick question about the 1 year in engineering industrial placement year in McLaren. So I'm currently a 3rd year mechanical engineering student. So I'm looking forward to apply for the placement year next year and head back to uni for a master program. So just want to ask if the placement is still open or for application.
I will need to double check, sorry. Let me just double check quickly. I think if it's not open, it will reopen at some point. So there is a yearly phase. And so what I would suggest, first of all, is just to subscribe to the careers website just to get the alerts on this. And I will need to double check if it's currently if the window is currently open. We know that the graduate scheme definitively is, but I'm not sure about the 1 year engineering placement. I'll have a quick check while we phrase the next question. Okay.
All right. Thank you.
Shi Chang, I'm really sorry if I say it wrong.
Thank you for the presentation. A little comment about the visa situation. I believe, I'm not sure about this, but I think there's a graduate route scheme available for international students who graduate from a UK university. I'm not sure, so there might be a possibility for us. I just have 2 questions. The first one is, going forward, how will the budget cap affects the size of the team, how it will affect the vacancy or opportunities? The second one would be, other than a master or PhD degree, what are some of the other skill sets, qualities you look for in a young engineer? Thank you.
Okay, so the effect of the cost cap, it has stopped us from growing the team further. To be honest, the thing is that it wasn't only the cost cap, but it was a cost cap at a lower level than what we had initially anticipated, because the overall level of the cost cap got dropped following COVID, because it was supposed to come into play at the same time. So it has had a bit of an effect on us. We've tried to limit the maximum the impact, and now we are getting back into hiring, but it has made it a little bit more difficult than it was a couple of years ago, to be brutally honest, to join an F1 team. Because the cost cap, and if we go back to the first slide, it will actually become it will go in steps. So we lose a little bit more budget next year and the year after. But I think we've made it in a way where we focus mostly on expenses that were not related to personnel, so that we kept the team and we still have the space to grow, and we've mostly tackled other ways to save money. So it is still a thriving industry. There's still a lot of people coming in, there's a lot of people coming out. It just made it a little bit more difficult, but it's never been particularly easy to get in. So it just, I think it is still completely possible, and we are still recruiting, and we have recruited this year still. And sorry, I forgot your first question.
The second one was about qualities that.
Yes. Okay. So in our team, I think because it is a highly specialized type of task, so we look at CFD as a whole, right? So from CAD to solution, and we look at optimizing it. All of us have a fairly strong background in numerical methods, etc. So there is this side that you need a certain knowledge on certain fields to do your job. But then after this, you just need curious people and hardworking people, and there's nothing really particular we are looking for, in the sense that it will be, so we typically have a fairly long discussion with all of the candidates, which is both about technical items, but also just more general questions. I don't think there is a specific quality that we request across F1, right? It really depends on the business as well.
The only I think maybe that is worth mentioning is for roles like as Julian mentioned, in CFD, which are very specialized, probably you are looking for people with high degree of knowledge in very specific areas, and that's why you will see many PhDs in highly specialized roles. On the other hand, if you are a fresh graduate and you are applying in the graduate scheme, I think be curious in an engineering sense. So be generally curious about science and engineering and be hardworking. I think it's also appreciated. I don't think that for the graduate scheme you are expecting people to have the ultra specialized, very detailed knowledge. It's more of an overall engineering understanding.
Right, I think we have time for like 2 more questions. Swapnil, I'm sorry if I mispronounced it.
Yeah, you pronounced it perfectly. Thank you. I just wanted to ask, means we have a graduate scheme here and the PhD scheme as well. So actually, I'm a MSc student and I fall in between them. Or we just have 1 year's course, for example, and we have the dissertation starting from the summer break. So we generally don't have time. But if a MSc student from aerospace who has a good background in CFD, means like we have CFD and advanced CFD in our syllabus. And if we are doing something, means if we are going for a dissertation on a topic which is like intensively related to CFD, then we do we have chance there, means after passing MSc and getting a good grip on CFD to get somewhere, means get a post related to some related to what to say, something in between the graduate scheme and the PhD scheme?
There isn't anything clearly defined at that state. So after this, yeah, never say never. But we've only done end of master project and something like this fairly rarely. But it has happened in the past, but probably it hasn't in the last 2-3 years, 3-4 years, I would say at least. Yeah.
But because I think you are referring also to general recruitment. Positions,
okay, sorry,
right?
It was
PhD is not, yeah, it's not a hard requirement. I mean, you can have an MSc and have a very good, solid background in numerics and CFD. Everyone is judged by the same people, but we are not short-sighted in just looking for people with PhDs, of course not.
And not everybody in our little team has a PhD.
Right, Rudvik.
Thanks. Yeah. Second, just my last and final question, which is so given, let's say you have a let's say a part 2-part configurations, which one of them is going to be put on the next race. How do you decide which is the part that will be put on using the whole aerodynamic tool set you have available with you, and considering that there are rules and things to follow? And is the project timeline for this upgrade decided much before, so like the start of the year? So let's say so let's say the Canada upgrade is decided at Australia, for example. Thank you.
Okay, there's a lot of questions there. Let's unpick it a little bit. So in terms of judging components, we need to trust our simulation tools, right? So the CFD and the wind tunnel environment, but we usually do back-to-backs for the components for which we have more uncertainty, or the ones that we want to validate. So we try to kind of do the cleanest on-track experiment. So track is our truth, right? That's the ground truth. And so we try to replicate as clean as possible a test in a track environment and use the sensors just to justify whether it's worth carrying over that part or not. We usually have predefined parts that we know will go to each event, and we'll judge them during the test sessions, and then we'll decide which one goes on for Saturday and which one goes on for Sunday. It will be even a bit different next year because we'll have to kind of define it a bit more beforehand. But yeah, typically that's how it would be judged in terms of when the parts are coming to track. Yeah, we are developing the car potentially 3 months or 3-4 months in advance, right? So we are reaching the point where we are going to freeze the geometry that will be defined for the launch, and as soon as we do this, then we'll start planning for the first upgrade, then the second, etc. So there is, if you think about this from the conception to the part arriving on track, there is going to be a serious amount of lag depending on the complexity of the part, right? So there are small events, and it has happened quite often in the past that you have as short as a week between the moment where you design something that is designed to specifically address an issue that you've seen on track. If it's a fairly small component, we sometimes bring we can go very quickly, so you can get a part on track the week after. But generally, if you think about something much bigger, like let's say a front wing assembly, something like this, you need to definitely plan it seriously in advance, and especially because it needs to go first through CFD, then potentially through internal, potentially iterate a couple of times, and then it will reach track. So it's a long process. So as soon as you've reached one milestone, you start to target the next one.
Amazing. Thank you so much. Thank you so much once again.
Right. Last question then. Swapna, do you have a question or? Okay. I'm guessing that's it then. Thank you very much for joining us. If you enjoyed it. Yeah, and I'll see you on the next Industrial Talk. Thanks very much, you guys, for coming over.
Thank you.
Thank you very much. Bye.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you so much.